Let's finish up the recording of this discussion, and then we will get into the lab. Yesterday, we continued with our discussion of thermal energies. And on Monday, we introduced the topic of thermal energy. What did we say thermal energy dealt with? What are we concerned when we're talking about thermal energy? Movement of what specifically? Microscopic particles, which we said could be atoms or molecules. Okay? That deals with what?
I thought we were getting away from all this microscopic.
Well, we're not going to talk about the atoms and molecules themselves, that's like what they look like, but we're talking about small things here, okay? So we're talking about the movement of these atoms and molecules that make up whatever substance. We talked about three terms on Monday. We talked about temperature, we talked about thermal energy, and we talked about heat. This discussion of calorimetry deals with heat. Heat, by definition, was what? Transfer of thermal energy, right?
From a hot substance
from a hot substance to a cold substance, high temperature to a low temperature. And we're going to make use of that fact today when we do our lab. Okay? So, in calculating how much heat or how much energy is transferred, we have to introduce a couple other terms. The term we introduced yesterday was specific heat or specific heat capacity. You'll see it both ways. Okay? What did we say the specific heat told us about a substance without necessarily reciting back to me the definition of it? What did the specific heat tell us about a substance? Chris, go ahead. So it talks to us about how easy or hard it is to heat something up or to cool it down. Okay? And we used a couple of examples like the sand on the beach and how the sand gets a lot hotter than the water does because of even though they get exposed to the same amount of sunlight, because it has a different specific heat value. The sand is much better at absorbing that energy and raising the temperature. Yes, Mary? Lower specific heats are things that are easier to change the temperature of. So in that case, the sand has a lower specific heat than the water does. Water has a really high specific heat. It is very difficult to change the temperature of the water. And I think we talked yesterday about the lake and how the lake stays. Did we talk about the lake yesterday? Okay. So, let's talk now. Okay. The lake is made of water. It has a real high specific heat value. Okay. It is responsible for one of our favorite wintertime events, the lake effect snowstorm. Okay. So, it gets cold in January. Maybe December, okay? And it's like 20 degrees. But does that mean the lake immediately freezes over? No, because the lake has a very high specific heat value. It's hard to heat the water up, but it's also harder to cool it down. So even though the temperature on the land may be very cold, the water still stays in the liquid state. So what happens is that air comes across the lake and it picks up moisture because the lake isn't frozen yet. Then that wind passes over the lake and gets onto the ground where it's cold. What does all that moisture then turn into? Snow. Okay? Because even though it's really cold on the land, it's not that cold over the lake because the water changes temperature at a different rate than the land does. Okay? We talked about the desert yesterday. So, well, a little bit, yeah, but more let's talk about the temperature. What happens to the temperature in the desert during the day? It's really, really hot. But at night, it's really, really cold. What is there none of in the desert?
water.
There's no water in the desert. Well, no water is kind of an overstatement, but there's very little water, right? Miriam, the sand and the other rocks and dirt and stuff in the desert have a much lower specific heat value. So it's very easy or easier to change the temperature of those things than it is to change the temperature of the water. Okay? San Diego. The temperature in San Diego fluctuates annually somewhere between 65 and 80. Okay? It never really gets colder than 65, never really gets warmer than 80. Okay? General. Okay? That's why the property in San Francisco is ridiculously expensive. San Diego, sorry, my bad. Okay. San Francisco is kind of the same thing, but San Diego is a little farther south, so it's a little warmer. If you've ever been to San Diego before, it's right on the ocean. Okay? Why doesn't the temperature in San Diego change all that much? Because of the water. The water has a very high specific heat value, which means it's hard to change the temperature of the water. If the temperature of the water never really changes all that much, does the temperature on the land really change all that much? Not a whole lot. Here we have kind of that effect, but our water is a lot smaller than like the ocean that San Diego sits on. Okay? San Francisco is very much the same way. San Francisco is on a peninsula, so it has water on three sides of it. Just a little bit colder water because it's farther north. So the temperature in San Francisco fluctuates between like 50 and 70. Okay? If it gets colder than 50 in San Francisco, it's kind of like, whoa, pick out the parka. Okay? But if it gets higher than 70, it's like, oh my God, the heat wave. So, because the water is surrounding the city, the temperature doesn't fluctuate as much as places like Nebraska. Okay? You watch the temperature in Nebraska in the summertime, it gets really, really hot in Nebraska, like into the hundreds. But in the wintertime, it can get pretty cold. Yeah, like the negatives.
I'm gonna live in Nebraska.
Really?
Yeah, I like.
Actually, no, from what I understand, the job market in Nebraska, Kansas is really good because farms are like making lots of money because people want their.
Well, I don't want to be like a farmer.
You don't have much other choice. You're gonna go to Nebraska. So, sorry, any Nebraska people.
Is that like biggest city, like Cracker Park?
Come on.
It's small.
It's maybe like Legacy.
Yeah.
Recording right now.
Anyway, sorry, Nebraskans.
Wait, what is the capital of Nebraska?
Wait,
is it
Lincoln, I believe. So, Lincoln. Exactly. So,
You know,
actually,
16th
when
president of the United States.
what?
I said 16th president of the United States.
He's from Illinois, though. So, actually, Sam, from what I understand, that Saturdays in the fall, when the University of Nebraska plays football home games, the football stadium is the third largest city in the state. Not even joking. Like the 85,000 people that go to the football stadium would make it to like the third largest city in the state. So,
Well, Ohio's not that big.
what? Come on. We have like
Wait, I don't know what that means.
that means that like there's only 2 cities in Nebraska that are bigger than like 85,000 people.
Oh.
Yeah.
Wow.
I mean, we have 3. Well, I mean, we have 3 that are pretty big.
Football. Big.
Columbus, Cleveland. Although Cleveland is, dwindling rapidly. So anyway.
There's a lot of gangs of our conversation yesterday. East versus West.
Where the shoes? Yes.
Oh, I think
Samsung. Is that like
That's their sponsor.
That's
Chelsea.
it's Ronaldo.
No, Ronaldo's on the opposite.
Where's Chelsea? Ronaldo is really
Chelsea's
Oh yeah, isn't Ronaldo and then other really famous guys supposed to be playing this year?
Ronaldo plays today.
Oh,
They
that's
played
today.
last weekend.
Who does
Oh,
David
who
Beckham
won?
play for?
They Ronaldo's team won
They did.
this weekend, yes. So
He's extremely.
Messi's the other
It was
guy.
the white team and then
The white team versus the red team.
Is David Beckham still playing?
Yeah, they played there.
Oh. Wait, who's your favorite soccer player?
So if I really have a favorite soccer player, it's probably just
I can still soccer player.
I like Taylor.
Alright.
Legend still is.
Let's talk about this, okay? Where does this all get us to? This gets us to this equation. And it says specific heat equation, but a better description of it might be more of the heat transfer equation. Okay? So Q is equal to M times C times delta T. Some of those things you probably can figure out what they are. What do you think M is probably going to stand for? Mass. What do you think delta T is probably going to stand
Change
for?
in time.
Change in temperature. Okay? So let's talk about the other parts. First, Q. Q is labeled as the heat. It could be the heat absorbed by a substance. Okay? But if some substance is absorbing heat, what also has to be true? Another substance is losing heat because of that whole conservation of energy idea. Okay? So it could be the heat absorbed by a material, but it could also be the heat that's lost by another material. Okay? Remember, we said heat. What was our definition of heat? Transfer of thermal energy, right? So this is how much energy one thing is giving to something else. Okay? Next. M stands for mass. Okay? Now, on your outline, there's actually a couple things that aren't right. The delta T is listed twice, and it shouldn't be. Okay? So one of those delta T's you can label as what? Change of temperature. The other one, change to C. C is the specific heat value. I didn't say scratch it out. I said we needed to change it. Okay, you said there's two delta T's
So
there.
the first one is C.
Sure. You just got to make one of them C. Okay? And then delta T stands for the temperature change. And we're calculating temperature change is always final minus initial, right? So C in that equation. C stands for the specific heat value. The specific heat value is a known value. It's either something that you can look up in a book for reference, or I tell you, or we measure it. And that's actually what we're going to do today. We're actually going to measure the specific heat value of a substance. Good. Use that for me. All right, are we good there? You are going to set yourselves up in just a second something called a calorimeter. A calorimeter is an instrument used to measure changes in thermal energy. And it works under the premise that heat, or thermal energy, flows from hot things into cold things until what? Until they are the same temperature. And then we refer to that as thermal equilibrium. Okay. How much energy flows from the hot thing into the cold thing?
Enough to make it.
Well, that equation that we just used. But it works under the principle of conservation of energy. If the hot thing is losing energy, what has to be happening to the cold thing? Gaining. How much?
The same amount that it
The
lost.
same amount that the hot thing lost. Okay? Are we good there?
Yeah.
So, what is a calorimeter? A calorimeter works like this. Okay, so here's a calorimeter. Styrofoam cup. And it has a lid. Yours has a lid over in the thing over there. Mine doesn't. Okay? So, we are going to put something hot and something cold inside of the calorimeter. The something hot, it could be a reaction, or it could just be a hot substance that we're going to use. Today we're just going to use a hot substance. There's some metal fishing line sinkers that are over in that water over on the side over there, sitting there getting all nice and hot. Okay? Then we're going to put something cold in there. You're going to use water. What's going to happen when we put the hot fishing line sinkers into the cold water?
You're not equal.
The fishing line sinker is going to do what?
Reach equal thermal.
Well, it's going to
equilibrium
cool
with the
down,
water.
and as a result of that, the water is going to
Heat up.
heat up until
Thermal
it's
equilibrium.
the same. Thermal equilibrium. Okay? So, something releases energy, something hot. Could be a reaction, or it could just be something hot. Then, that energy flows into the cold thing. In this case, we're going to use the water. Why do we put it in a styrofoam cup?
Because it's 12 ounces.
So now, when we're measuring the changes in energy, what are we only looking at as far as the transfer of energy goes? What's inside? We have this nice insulator to keep all the outside heat from entering in, staying outside. So we can just focus on what's going on inside. Okay? Does that make sense? And that's what we're going to do today. Questions relating to heat transfer, how do we calculate the amount of heat transfer, the calorimeter, et cetera, et cetera. In theory, yeah, although not enough heat to proceed. It's really not getting that hot in the big picture, you know. So,
How hot is it?
well, where is it?
Can we touch it?
No.
Where is it?
It's sitting in those beakers of boiling water over there.
Oh, okay.
Just go ahead.
So how do you have a temperature? Like when it gets to the city?
We'll talk about Good here? Questions? Alright, let me do this. We stop our recording.